So we have a beam is made of steel. We have an allowable stress of 24 KSI. We want to find the largest internal moment that the beam can resist if we apply a moment about the z-axis, so going that way, and about the y-axis, twisting that way. And it's symmetric, so it could be one way or the other, doesn't matter. So we know our equation for stress due to a moment is stress equals mc over I. So we're going to have to do this twice. Once using the moment inertia about the z-axis and once about the y-axis. So we'll start, first we want to find the largest moment. So let's rearrange this equation. So solving for m, we get m equals stress times moment inertia, whether that be z or y, over c. So start off, we'll find moment inertia about the z-axis. So because this shape is symmetric and whatnot, we can do a few tricks here. So if we draw our shape, we got one rectangle at the top, one in the middle, and same on the bottom. So if you remember, moment of inertia is the sum of, if you have all rectangles, it's just bh cubed over 12 plus AD squared. So we could say this is shape 1, this is shape 2, and we'll do 2 times shape 2 because that's the same shape. That'd be fine. There is an easier way to do it. We can call this outside shape all the way around the outer edges, shape 1. And that would be 6 by 6.5 inches. And then we can call this shape here shape 2, and we'll void that out. We'll subtract that. And by doing that, all of my centroids are through the centroid of the whole shape, which means our AD squared term is 0. So it makes it a little bit easier. You don't have to do it that way. So for moment of inertia about the z-axis, which is this axis here, we'll get our first, which is our outer, which the base is 6, and the height is 6.5 cubed over 12. And we're going to do minus, we have 2 of these, one on either side, so 2 times this height here is 5.75. Or no, the width here is 5.75. The height is 6 inches. So we get base is 5.75 times the height of 6 cubed over 12. And for that, we get 33.8125 inches to the fourth. So now we can plug this in. So our moment equals our allowable stress, which we know is 24. Moment of inertia we found to be 33.8125 divided by c. So this is just the point where we're trying to find the stress at. So it's always going to be from the centroid. So from here up, or down really, doesn't matter. So if we wanted to say find it at this seam here where those connect, we could plug in that distance. But we want to find the max stress, so we're going to go as far out as we can, because with a moment, the maximum is always going to be the farthest out point. So right there. And that distance is going to be 3.25 inches. So over 3.25, we get 20.8 kip feet. So now we can do the same thing, but about the y-axis. So I sub y. And in this case, it gets a little bit different because we're going to turn our cross-section sideways. So we can look at it like this. And what you'll notice is that Before, this top rectangle, the centroid was off the centroid of the main shape. But here, all three of these shapes, the centroid is about that y-axis. So I'll call this center rectangle shape 1, and these outer ones shape 2, and we'll just multiply it by 2. They're the same shape. So we get shape 1 has a base of 6 inches, a height of 0.25, plus 2 times shape 2, which has a base of 0.25 and a height of 6. So we get a moment of inertia about the y-axis to be 9.0078 inches to the fourth. So plug that in again, we get moment equals our stress, 24, times I, 9.0078, over C. So in this case, it's going to be to the highest point here, which is right here, or right here, same thing, and that is 3 inches out. So we get 6.00 kip